everyone, welcome to our presentation for SCUDEM 2024, Problem C, Standing Against a Mammoth. We are Team 1016 from the University of Florida, consisting of Deja Antoni F., myself Yanxiang Shan, and Daniel A. Soto. Our coach is Youngmin Park. Today, we will explore the extent of the damage that a spear can inflict on a mammoth through an analysis of the kinematics of both the spear and the mammoth. Our objective is to compare the methods of the throwing and bracing to determine which method is more effective in inflicting damage. Additionally, we will apply special geometry to analyze how changes in the spear's shape affect the inflicted damage, allowing us to determine which scenario the claw-based spear is better suited for. Our study revolves around two main questions. How does the change in the shape of the spearhead affect the air resistance experienced by the spear? And how does this change in the shape impact the amount of damage inflicted on the mammoth? To answer this, we developed two mathematical models to analyze the scenarios of throwing and bracing and calculated the amount of damage the spear can inflict in each case. For our modeling, we made several simplifying assumptions. The first one is the spear does not rotate or spin during the throwing process, and we will only focus on the spearhead and ignore the shaft. The mammoth remains stationary in the throwing scenario, and the spear will not break before inflicting full damage. And the last one is the spearhead is treated as a three-dimensional geometric figure composed of 5 vertices. To better understanding the geometric property of the spearhead, we use a Cayley-Wenger determinant to calculate its volume and cross-sectional area. This allowed us to analyze the spearhead's volume and the cross-sectional area change with varying x, y, and z coordinates and impacting its overall performance. And here are the 3D models we generated by the Python. And the left one is about how does the volume change with the varying x, y, z coordinates. And the left two are how does the vertical cross-section areas and the horizontal cross-section area change with the varying x, y, z coordinates. And in the throwing scenario, we generated differential equations describing both horizontal and vertical motion. These equations incorporate parameters such as the mass of the spear, velocity, and the air resistance. For the bracing scenario, we simplify our approach by assuming the mass and the velocity of the mammoth are constant. And finally, we measure the damage inflicted by the spear on the mammoth using the kinetic energy represented by the formula here. Kinetic energy equal to half times m times the u. U is u squared. U is the final velocity.
So next, I would like to take you through our model implementation. So we used Python 3 to code our solution, and we used the NumPy and Matplotlib libraries. Here are a few of our absolute constants. So these do not change at all within our simulation. We have things like the air drag coefficient, gravitational acceleration, density of air, other constants of those sorts. These are all in SI units, so meters, seconds, kilograms mostly. And here are a few of our iterable constants. So like length, width, and height of the cone, these range from 5 to 20 centimeters. The initial velocity was ranged from 15 to 30 meters per second, and theta was ranged from 0 to 90 degrees. Here are our kinematics equations. So Fdx and Fdy are the net forces in the x and y directions respectively. These are very similar, but Fdy has that additional factor of mg because of the gravitational force. So using Newton's second law, we calculate the deceleration over that small period dt, which in our case was 10 to the negative 4th second. And then we calculate the new velocity based on the last velocity and the deceleration over that period of dt for both the x and y directions. Now Sx is the position, and we assumed that over that small time period dt, the velocity is constant, so we could use the v equals s over t to calculate s and append it to our list of all x and y positions. Here are the descriptions of all these variables. So Fdx, Fdy I already said are the net forces. Vx and Vy are the vertical and horizontal components of the velocity, and Sx and Sy are simply our positions of the spear. So here's a example spear trajectory for v equals 15 meters per second and theta equals pi over 4. It is important to note that only trajectories that intersected with the mammoth, so resulted in a direct hit, were actually categorized as valid and therefore used in our simulation, because there's no point in calculating things like the lethality when the spear didn't even hit the mammoth. So as I said before, the model was run for width, length, and height from 5 to 20 centimeters. And assuming the spearhead actually hit the mammoth, the lethality was calculated. So here is our lethality function. First, delta E is simply the final kinetic energy of the spearhead right before it hits the mammoth. So it's simply 1/2 mass over 1/2 mass V squared. And then the force was delta E over the spear height. Now, we used this formula because simply pressure doesn't give enough insight into the actual lethality, because if you pierced the mammoth with an eel, the pressure would be really high, but the lethality would be basically 0. So we used a combination of both energy and pressure to determine whether the hit was actually lethal. So the force is equal to delta E over the spear height. This is because the change in energy is simply the work done, which is the F, which is the force times distance traveled. And we just assume that the distance traveled is the actual height of the spearhead. And from that, we can calculate pressure as that force over the bottom dimensions of the spearhead. Here's the model implementation for the charging conjecture. So first, the mass of the mammoth. We averaged two figures to get a more even value. And then we varied the velocity of the mammoth from 0 to 9 meters per second, and then calculated the kinetic energy of the mammoth as before, 1/2 mass times velocity squared. Again, energy and pressure were both returned as a metric because high pressure doesn't necessarily imply high lethality, but if the pressure and energy is high, then that gives us a pretty good metric that the lethality was high. So here are results. So on average, the thrown model worked much worse than the charging model. The thrown model only had an average of 1.2 kilojoules with a minimum of 0.05 kilojoules, which is 50 joules, and a maximum of 10.5, 10.6. While the charging model had an average of 187 kilojoules with a minimum of 69 kilojoules and a maximum of 364 kilojoules.
So for our sensitivity analysis, we used the Python library salib. And to generate the samples for our sensitivity analysis, we used the cell-to-sample method from this library. And to get the analysis itself as well as its values, we used the sobal.analyze method. Now, for the analysis for our thrown model, it tells us that the initial velocity has the least effect on the final damage that we do. And second to that is the spearhead shape. And the spearhead shape actually does not affect the final damage that much, although it does slightly more than the initial velocity. And this answers our second question, which is whether the spearhead shape affects the final damage. It doesn't seem to that much. Now, the parameter that does affect the final damage the most is the angle of the throw of the spear, which is theta. Now, for the charging model, we see that the final velocity is the parameter that matters the most in terms of maximizing damage. And compared to mammoth's mass, and this makes sense because if you look at the kinetic energy formula, we see that the velocity term is squared. So small changes in velocity are going to matter more than small changes in mass, despite how big mammoths can be. Now, for the limitations of our model, our thrown model does not account for the rotation of the spear as it flies. So an example of how this could be limiting is if you consider this is the mammoth and this is a spear. In real life, if you were to throw a spear like this, and it happens to hit the mammoth at an angle like this, it might not pierce it well enough and it might scrape. But if our model were to hit a spear at this angle, or to hit a mammoth at this angle, it would do like this. And that would return probably more energy than in this case, which wouldn't be ideal. We would want to model something that would account for edge cases like this, and our model doesn't do that. The other limitation is that our rectangular pyramid model, which simplifies the shape of the Clovis point to just a rectangular pyramid, may not approximate the shape of a Clovis point well enough. That's something we can look into in the future. We also don't take into account whether a human is capable of propelling a spear at given dimensions, but we chose reasonable masses for the spear, so it should be possible, but it's a minimal effect that could be modeled. For the charging model, we also didn't model the risk of a human getting trampled during the baiting of the mammoth, because you can imagine that is a very risky thing that you could do. And there are ways that we can handle that. And in both models, the possibility of the spear breaking was not considered. That's another thing that we can improve. For future work to maybe help some of these things, for example, namely the shape of the Clovis point, we could import a full 3D model of the Clovis point and use the Cayley-Menger determinant formula to calculate its cross-section areas so that we can accurately model its path with air resistance. Also, we can, to deal with the risk of the human getting trampled as they bait the mammoth in the charging model, we can use a stochastic model to measure the reaction time. So we can model the interaction between that model and the time at which the mammoth gets towards a certain distance of the spear, and that will determine whether the human survives a given interaction or not. Thank you for watching this video.